In this video, we will be taking a look at quantum physics. Quantum physics is a branch of physics that deals with the behavior of matter and energy at the atomic and subatomic level. It was first developed in the early 20th century to explain the behavior of light and matter at the atomic level. Unlike classical physics, which describes the behavior of objects on a macroscopic scale, quantum physics describes the behavior of particles on a microscopic scale. The uncertainty principle. One of the most important principles of quantum physics is the uncertainty principle. This principle states that it is impossible to simultaneously determine the exact position and momentum of a particle. This is because the act of measuring one of these quantities affects the other. The uncertainty principle has profound implications for the behavior of particles at the quantum level. Wave-particle duality. Wave-particle duality is another important principle of quantum physics. This principle states that particles can exhibit both wave-like and particle-like behavior depending on how they are observed. For example, when a particle is observed, it behaves like a particle, but when it is not observed, it behaves like a wave. This principle is central to understanding the behavior of particles at the quantum level. This principle is central to understanding the behavior of particles at the quantum level. Wave-particle duality is a fundamental concept in quantum mechanics that describes the behavior of particles as both wave-like and particle-like. It is one of the most important and fascinating aspects of quantum mechanics, and it has profound implications for our understanding of the universe. In classical mechanics, particles are treated as discrete objects with well-defined positions and momenta. However, in quantum mechanics, particles exhibit wave-like behavior and are described by wave functions that represent the probability of finding the particle at a particular position. This means that particles do not have well-defined positions or momenta, but rather exist as probability waves that are spread out over space. One of the most famous experiments that illustrates wave-particle duality is the double-slit experiment. In this experiment, a beam of particles, such as electrons or photons, is passed through a screen with two narrow slits. On the other side of the screen, the particles form an interference pattern, which is characteristic of waves. This interference pattern can only be explained if the particles are behaving as waves that interfere with each other, rather than as discrete objects that pass through one slit or the other. Another experiment that illustrates wave-particle duality is the photoelectric effect. In this experiment, light is shown onto a metal surface, and electrons are emitted from the surface. The energy of the emitted electrons depends on the frequency of the light, but not on its intensity. This can only be explained if light is behaving as particles, or photons, that transfer energy to the electrons. Wave-particle duality has important implications for our understanding of the universe. It means that particles are not simply discrete objects that move around in space, but rather are complex systems that exhibit both wave-like and particle-like behavior. It also means that the behavior of particles is inherently uncertain, and that the universe is inherently probabilistic at the smallest scales. Wave-particle duality is one of the key concepts in quantum mechanics, and it has many important applications in fields such as quantum computing, quantum cryptography, and quantum field theory. It continues to be an active area of research, and scientists are constantly uncovering new and fascinating aspects of this phenomenon. Quantum entanglement. Quantum entanglement is a phenomenon that occurs when two particles become correlated in such a way that their states are dependent on each other. This means that the state of one particle can affect the state of the other particle, even if they are separated by great distances. This phenomenon is at the heart of quantum computing and has important implications for cryptography and communication. Quantum entanglement is a phenomenon in quantum mechanics where two or more particles become correlated in such a way that the state of one particle is dependent on the state of the other particle. This correlation exists even if the particles are no longer in contact with each other, and it persists instantaneously, regardless of the distance between the particles. This is known as spooky action at a distance, and it is one of the most fascinating and counterintuitive aspects of quantum mechanics. Entanglement can occur between any two quantum particles, such as photons, electrons, or atoms, and it is created when the particles interact in a way that results in the creation of a shared quantum state. Once entangled, the particles become part of a single quantum system, and any measurement made on one particle will instantaneously affect the state of the other particle, regardless of the distance between them. The concept of entanglement was first proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935, as part of an argument against the completeness of quantum mechanics. However, it was not until the 1960s that experimental evidence for entanglement was found, and it was not until the 1980s that it became possible to reliably generate and manipulate entangled states. Entanglement has important applications in quantum computing, quantum cryptography, and quantum teleportation. In quantum computing, entangled states are used to perform calculations that are faster than classical computations. In quantum cryptography, entangled states are used to generate unbreakable codes that cannot be intercepted by eavesdroppers. In quantum teleportation, entangled states are used to transfer the quantum state of one particle to another particle over a large distance. Entanglement is a crucial aspect of quantum mechanics, and it continues to be an active area of research. Scientists are exploring new ways to generate and manipulate entangled states, and are working to understand the fundamental properties of this phenomenon.